So welcome back, nerds. Today, calcsters. All right, looking at stuff. We get to start chapter 4, section 4 today. And we are going to continue putting stuff together here. Chapter 4.4, we've already kind of seen some of it, but we're going to readdress it. We're going to talk about local extrema, which the only other extrema that we've really looked at in detail, we looked briefly at if a function goes from increasing to decreasing, then it means there's going to be a max, but we didn't really formally define it. The only extrema that we've truly seen is the absolute extrema, where it's either the critical number or the endpoints, and then we just check those. So we're going to zoom in on the local extrema today, and then we get to talk about a new word that I'm not sure if you guys have seen. Local extrema and concavity. Have you guys seen concavity before? It makes me think of geometry, because it looks kind of like concave, right? So we'll get to this point eventually. This is going to take us a couple days to get through, just so you're aware. But concavity in its most basic is what Sean was trying to show. How does it curve? This is a different type of curve than this. Now, more than just because it's increasing or decreasing, but the other day when we wrote one, we said we know it increases. Do you recall when we talked about, does it increase like this or does it increase like this? Like we drew those two pictures. These both increase, but they have different concavity. It's just how it bends is how we talk about concavity. We'll get there, but we're going to do local extrema first. So to start today, our first topic, I should probably have some notes, but we'll get them here in a minute. We're going to define for ourselves a lovely theorem to start. And we're going to call this theorem the first derivative test. And this is just a formalization of what we've done when we're looking at intervals of increase. Now, this is a theorem. I'm just going to call it a theorem here. We're going to present it as such, but we're not going to prove it. That's the job for analysts. So here we are, the first derivative test. What does the first derivative of a function tell me about it? Like we've been using it in the last section. It tells me something. The slope of the tangent, for sure. That's what it tells me. But very specifically, when we put those on a number line, it tells me when my function f is doing one of two things. Either it's increasing, it's decreasing, I guess three things, or it's constant, right? Those are the only three options that my first derivative is going to give me. So all we're going to do here is we're going to generalize that to make like a real solid definition. And if you want to do a part of the proof, we can, but I'm not going to make us. So here we go. We're going to be more rigorous with this than we normally are. We're going to let f be a function on some interval I, on an interval. And I wish I had a good way to write italic stuff. We're just going to call our interval I. So from A to B, don't know, it's just an interval. Okay, now, as we look at this, we're going to say, suppose, and we're going to get a few different things, that C is a critical number of F. And I'm going to pause here for just a second because it is easy to get goofed up. When we find critical numbers, it's by setting the derivative equal to 0, right? But if we have some function f and we differentiate it and get the critical numbers, they are the critical numbers of f still, even though they came from f prime. So a weird little language thing, but f and f prime are certainly related. We're answering questions about the original function f. So C is a critical number of f, and specifically, we're going to say AB, A comma B, and rather, A comma B is an open interval in that bigger interval I. So all that this is saying, and it looks ugly, but it's really just the formalization of it, is that if you pick some range of numbers, here's I, from this finger to this finger, is there a smaller range inside of it? That's what we just said. Here's some smaller range between these. So imagine a segment. Somewhere in the middle, we can make a smaller interval. Okay, now the real language that we're going to use if we were doing this hardcore is we would call it a neighborhood, but I'm okay with just calling it some open interval. Okay, here we go. We get some interval in I, and we're going to say containing C, just before I forget it. So C is between A and B in this bigger interval. Okay, we only get three possibilities. We're going to say, I think we make this nicer. here we go. If, three possibilities, f prime of x is greater than 0 for some value x between a and c, for a is less than x is less than c. So we're finding this value between these guys. And then furthermore, and we're going to summarize the next two much less formally than this. But let's say it's positive derivative here, and f prime of x we'll say is less than 0, somewhere between c and b. So we're looking at in that middle interval for x is greater than c, but less than b. And we're going to pause here really quick because I can already tell the furrowed eyebrows make me have a little concern. Here's my challenge. I'm going to give you guys about a minute. I want you to really roughly in your margin, try to sketch what's going on here. That's your goal. You can sketch f prime if you want. You can sketch f if you want. But I want you to try to sketch what's happening here. I'm going to give you a moment. I don't care if you're wrong or right. Like, I hope you're right, but obviously it's okay if you're wrong. I just want to see where your mind and what your minds do to make sense of this. So try to sketch this situation. I'm going to do it up here too. Should we do this just as a whole class? Is everybody sitting there not a clue? Okay. So I'm just going to draw a coordinate plane. That's fine. And we can just sketch this. It's okay. I wouldn't have it like in the theorem. I just want to make sense so we can see what this is. Okay. Do you want me to sketch f or f prime? F. I heard both, so that's okay. We'll do both. I'm fine with that. Check it out. F prime of x is positive. So here's some interval, and I'm just going to say here's my interval I from here to here. This whole range is that larger interval I. And I arbitrarily, like purely by chance, does it include the origin? It could or it couldn't. Mine does, because it's going to be nice to graph. So here's some range of values that we'll call the interval I. Now in here, there's an A and a B. So I might put it like here, and it's open interval, so I'm just going to use parentheses. There's my A to B. So we have a function that's going to be defined on that larger interval, and in there, there's a critical number of f, and A to B is in between here, and C is somewhere in here. Okay, arbitrarily, I don't care where it is, you just hoot and holler where I'm at C. Okay, so here's my critical number, C. Okay, now in this case, it's a 0 of my derivative, but it could be undefined, right? So I'm going to use a 0 example. Now, if I'm looking at this, there's an x value between A and C, and there's a bunch of them really, but f prime of x between A and C is positive. So I don't care how positive it is, I'm going to be really lazy with my derivative. It's not going to be an interesting one. I'm going to just say, hey, it's positive. Do you agree that my function is positive right here? Up until we get to C. Now, just to check, because I can see the eyes, somebody misinterpreted the statement there. Is the slope of this positive? No, but that's not the question, right? Is my function right now, is it above the x-axis between A and C? That's it. And that's what this part says. We just did this. F prime of x is positive between A and C. And then I know additionally that f prime is negative here between C and B. So I'm going to do the boring version. Is my function now negative between C and B? Now, this is f prime. And we're going to do a really lazy sketch of this, but help me out here. If we tried to sketch from f prime, this graph that matches this, could we sketch f? Could we go the opposite direction? I think so. Right here, without a number line, we're going to try it. Is my function going up like this or down like this? F. If my slope is positive. It's going up like this. Now, as I go further, does my slope get bigger or closer to 0? So what I'm thinking in my head is it has a positive slope and it starts kind of slowing down. So I'm thinking something like this, like a half of a parabola. Okay, so I'm going to sketch that just really roughly, and we're going to see if you guys can reach the conclusion here. Let's say it does this, so it's pretty positive, and it's getting less positive, less positive. My slope is what I'm talking about, until it gets to 0. So here's a really positive slope matching with this high point. Here's a less positive slope matching with a slightly lower point, and it just keeps doing that until we go all the way down. Okay, On the other side of this, if my derivative is now negative, it means all my slopes are going to be what? And do we agree it's only a little negative right here? Okay, so it's only a little negative. As I go further, does it get more negative? Which means my graph, if its slope is more negative, does it get steeper or less steep? It keeps getting steeper. So this essentially looks like this. Okay, from this, what do you think we've just found? Have we found an extrema of some sort? What did we find? Is it a local, like, and because we don't see, like, could the function exist way outside of this interval also? Like, we only looking at this little spot, right? Some little neighborhood is what we're looking at. Is this a local? Could it be an absolute? Do I have any reason right now to think it's absolute? Like, based on what I can see, it's the absolute part of this section of the graph. But if the graph goes forever, could it do this again? And I just don't know it because it's not in that interval. So I'm certain that it is a local, and maybe it could be a like total absolute, right? So what's our conclusion? If we see the derivative here do this, what happened at C? Then the point C, comma, f of C is a local, and I'm going to put it in parentheses or brackets. What's the alternative word we could use? Local or not absolute? Relative. Max. Okay, this is a very rigorous definition. Now, when you hear the word rigor, and I imagine you've heard other teachers say it, do you know what it means to be rigorous? Thorough, maybe. In mathematics, it's much more specific. Rigor in math means there's no ambiguity. Like if I just said on some interval, like we don't know where it is, right? But if we define it now, it's much more specific. Even though I still don't know where this is, I can tell you exactly what an interval is, right? Like we have to have that thorough, I like that word for that, by the way, Sean. We have to have that very clear and thorough definition of what it is that we're talking about. That's what makes math rigorous. Okay, so looking at this, can you help me reword this easier? And we're just going to do an IE, which, do you guys know any Latin? Now you will. IE is id est, which means in essence, essentially is what we're thinking of it. Here's another way to say this. Now, this is a very formal mathy definition. Can you help me write this in layperson terms? Somebody who's not doing rigorous mathematics, how would you explain this idea? If f prime does what? What happens with f prime here? It changes. Something about it changes. It does go over the x-axis. I agree with you. What, like on this side of the x-axis, what is f prime? Positive, and on this side it's... So check this out. In the standard like everyday language, I'm going to change this to green just because it's a nice little addition. I'm going to do the other two like this if you're okay with it. If f prime changes from positive to negative. If I was increasing and now I'm decreasing, we must have had a maximum. Like, and that's the gist of this idea, and that's exactly what's written here, just in nicer language. Have we already been using this? Like we haven't used it formally, but have we talked about this? Okay, what if I wanted it instead, and we're gonna do, unless somebody's opposed, we can do the rigorous definition if you guys want for the other one, but I'm also okay with if we can make it our own layperson, just nice words, we can just use that. How would I find a local min? If f prime changes from, if I had a function that was decreasing and now it's increasing afterward, did I just find a minimum? Yeah, we had to. If it changes from negative to positive, we have a what? Good. I'm going to use local just because it's shorter, but we get a local minimum in that situation. Now, we could do the same rigorous definition, but for all intent and purpose, I think that since we already have this concept in our head, this is nice to formalize if you're going to study mathematics at a deeper level, but this is the meaning of it. Okay, there's a third situation. What could happen? It could be positive to negative, or it could be negative to positive. Have you ever seen a function that is positive and touches the axis and it's still positive? in that situation, f prime doesn't change sign. And it doesn't matter if it's up here like this, they're both positive, or they're both negative. If f prime doesn't change sign, do we have an extrema there? What do you guys think? If I'm positive to positive, I have a function that's increasing, then it's increasing. Was there an extrema on this graph? So if f prime doesn't change, no extrema. This is the first derivative test, and we've been almost using it this entire time. We haven't been asked to find the actual local extrema, but I have been talking about when is it increasing and decreasing, and then we've even used this picture to make sense of it. This is what this theorem is really formally defining. Okay. Feels okay, feels awful. Okay. Is it better with this language? Okay. So let's use this. And here's the deal. There's not a whole lot new here right now. Like, we've been using these same ideas. I want you to try one problem for me by tomorrow. So here's what I want. I want us to find local extrema, which, remember, in absolute is still local, for, or of rather. And here's our first one. We'll do another one at the start of class tomorrow. I'm going to give you one right now. I just want to see what you guys do with it. Let's say f of x is x cubed minus 3x squared plus 5. Now, I never talk about it in here. Your book doesn't do it this way. When I do these, and hopefully when you do them, I'm going to use a number line rather than an ugly table. I would use a number line just like we have been doing. Your only job this evening is to find me the local extrema of this function. Cool. All right, CAL, see you later.